computational learning theory conference, or COLE. And every attendee in conference, if you've been to one, you know that every attendee gets a badge with your name on it and your affiliation. People who signed in at the registration desk for the 94 instance of COLE got a name tag with a name, affiliation, and a plus or a minus next to their name. And only one person knew how these labels were generated, and that was this guy, Haim Hirsch. He was the organizer of the conference, and the only guarantee he was willing to make was this function, that was hidden function that was used to create this plus or minus label, uses only the name of the attendee and nothing else. And really the goal was, you guys claim to understand machine learning, let's see if you can figure out this magic function that I used. And there was another slight bit of a hitch. People were supposed to, nobody was given a list of names with plus or minus. People had to go talk to others and look at their name tags and find out what the label was. But we know that's really hard for computer scientists, so we won't do that. Here's a slice of the data, and I'm showing you only 6 names, and 2 of them have labels. Claire Carty is minus, Peter Bartlett is plus. So now the question to you guys is, how are these labels generated? I've given you training examples, and pretend that you're attendees of this conference, and your job is to figure out, either tell me what's the function that was used to generate these labels, the plus and the minus, or tell me what's the label for my name.
Your label's minus.
Why?
Because the first letter of your first name is not equal to the first letter of your last name.
First letter of
No, the label is, if your first name, second letter is vowel, it's positive.
Okay, that's one function.
We need more information.
We need more information. So I'll give you more information. I'll give you labels for the others as well.
Odd numbers have.
And good. So as long as there's disagreement in the class, I'm happy. There's room for this class. If you want, the full data is on the class website, and you can stare at it and you can tell me what the function is when we meet again. And in some sense, what you guys are doing right now is what we are hoping from learning algorithms. The learning algorithm gets a list of examples, and there is this oracle or nature or something that has a function and is refusing to part with it, except through this very limited channel. And the learning algorithm's job is to figure out what the magic function is. And it must be obvious to you at this point, from at least these examples, there are many functions that can fit your data. Odd and even, think about the second letter, first character, something. So in some sense, the fundamental question that we are hoping to tackle is there any hope for learning? There are so many functions that can fit this, that can produce these pluses and minuses. How do we hope to understand what is this magic function that some random guy came up with the day before the conference? And in some sense, if you think about it, that's what we are hoping learning does. So what is machine learning? Before telling you what is machine learning, I want to point out that whether you like it or not, machine learning is everywhere. You've used it. So if you ever used email in the last decade, you've used machine learning, because there's a spam detector that looks at an email and says spam or not spam. If you use Facebook or Google Plus, Photos, whatever they call it today, typically if you upload a photo, it finds people, puts a box around faces and asks, do you want to name this person? How do you know there's a face in those set of pixels? There's a classifier sitting there. And Amazon or Netflix, if you like these movies, you might like this one too. Or if you bought these things, you might want to buy these other things. These are all classifiers. If machine learning moves around billions of dollars in the form of algorithmic trading. Handwriting recognition, if you've ever deposited a check that uses handwriting recognition and you found that it really does not work, you have machine learning to blame. Google and Facebook make billions of dollars, their entire revenue is based on ads. And who decides what ads you see? There's a learning algorithm, there's a classifier sitting there. It seems like it might be an interesting use of machine learning to decide whether you should take an umbrella tomorrow or not. If you've used Google Translate, it brings people together because I'm able to read Dutch newspapers. Not sure why, but I read it. If you've ever used Google Glass or Google Now or Siri or any of these things, how on earth can a program possibly understand what you're saying, let alone do what it has to do based on your actions and your location? Because there's a classifier sitting there. Google's trying to get a car out that can drive itself, and you know where I'm going. There's a classifier sitting there. There's some talk about a flying helicopter. One of the coolest applications of machine learning, and probably one of the most important ones maybe in the coming decades, is applying it to medicine, identifying diseases and drugs that cure diseases and things like that. So learning is everywhere. Still haven't answered what is machine learning. Let's try to define machine learning. So I've given you a bunch of examples of the kinds of programs that qualify as products of machine learning. What could machine learning possibly be? What is machine learning?
Learn from each of the instances and then derive a logical sense of each of the thing and then classify your direction.
Okay, so I heard words that are saying something about instances, something about logically what?
Yeah, instances, logical description,
Okay.
or logical function that derives those things and act as a classifier.
So you train a classifier based on instances. Okay, that's an answer, and that's a legitimate answer given the examples I've given so far. Let's look at the history of it. I'm a big fan of history, so let's look at history. Probably, to my knowledge, the first use of this phrase, at least in CS circles, was in a paper by Arthur Samuel. And what he wrote was, it's a field of study that gives computers the ability to learn without explicitly being programmed. Or at least that's what he's supposed to have written. I did some research, and it turns out he didn't write exactly that. He wrote a paper in 1959 titled Some Studies in Machine Learning Using the Game of Checkers. And he said, programming computers to learn from experience should eventually eliminate the need for programming effort. Kind of an ambitious goal. But if you think about it, this is more of a philosophical statement. It doesn't tell you anything actionable. This is not a well-found problem yet. Herbert Simon, 1983, he said, machine learning or learning denotes changes to a system that are adaptive. And what does adaptive mean? Adaptive changes are the changes that enable the system to do a task better the next time it does the task, more effectively. By the way, Herbert Simon is probably, to my knowledge, the only guy who got a Nobel Prize in Economics and a Turing Award. So he's a smart guy. And to me, this definition is interesting because he talks about something that the previous definition does not mention, which is learning is generalization. You're not learning something if you do not generalize. Otherwise, you're just memorizing something. If you're and the task never changes, you've not learned anything, you've just memorized something. If I ask you what's the capital of Japan and you say Tokyo, and you get a point. Now I ask you again, what's the capital of Japan, and you say Tokyo, you should not get a point. You're not learning. This idea was popularized by Tom Mitchell, roughly the same sense, but slightly using more symbols, let's say. And Tom Mitchell talked about a well-defined task. Let's say you have a task or tasks T, and you have a mathematical definition of a performance measure, let's call it P, and a mathematically formal definition of something called experience. We'll talk about what it means. A program is said to learn if, as experience is increased, its performance in the task T, improves objectively according to the performance measure P. So this is about as well formed as we are going to get a definition of machine learning. So if you are hoping for a definition of machine learning, roughly this is about as much as we can get. But I hope the general idea is clear. Learning is essentially a study of generalization and nothing else. If you do not generalize, you're not learning. So it's not just doing well on the instances that you've seen before. So if I gave you a list of examples with pluses and minuses, names, and I asked you what's the label for the third row, and you look it up and you say it's a plus, big deal, I can do that. And we know how to do that. There's nothing magical involved. What makes it interesting is if I ask you to, given those 6 names, I give you a new name that you've never seen before, and you're still able to label it. So why bother? Why study learning at all? If you ask me, my primary interest is it's the most interesting part of computer science. It's awesome, but I probably need to convince you a little more. Or maybe not, you guys are already here, so. So why study learning? Learning is, another way of thinking about learning is it lets us build applications, computer programs, that have capabilities that were not explicitly programmed into them. If I have a compiler, it can compile programs. It can compile languages, programs in a language that it has never seen before. On the other hand, statistical parsers can parse any English text, even text that have never been uttered before. And they don't necessarily have to belong to a valid grammar. Another way of motivating the study of learning is it lets us understand biological learning. And this is kind of a hacky claim because who said what, it's not, we have no idea what's going on in our brains, but maybe understanding mathematically what learning is would let us define, I don't know what's going on in the brain when biological learning happens, but at least these things are not happening. Another motivation to study learning is to study teaching. Because you can think of yourself as a programmer not writing a learning algorithm, but actually you are the teacher and you're teaching the program to recognize cats or whatever. And I truly believe, and you might call me biased, I truly believe that machine learning is the future. Because it lets us build systems that that can actually encounter situations that they've never dealt with before and still do something reasonable. And that's my preferred way of thinking about learning. Say I want to write a program, I want to write a cat detector, and in photographs, not in real life. And I have no idea how to detect cats. I can describe cats, it's got a face and ears and stuff, and it's got a tail. But I have no idea how to write this program. If I had to write a program that detects whether a number is even or odd, I know how to write that program. But a cat detector is hard. And it's hard because of multiple reasons. A, there's going to be noise in the data, in the examples that come in. And B, I really can't define this idea, the idea of a cat. I can detect a cat as a person, but I don't know how to write the program. Or, say if I want to transcribe speech to text, and I have to write a program for that, I can give you certain hints as to how to do that, but I can't really write the entire program, especially I can't write one that will do well on text that you have never seen before. And these are the kinds of situations where learning is going to shine. And seen from that perspective, learning is a new way to think about programming. You're building programs that build programs. And as a result of this property, which is you can deal with unseen data, unseen inputs better, programs that are built on learning tend to behave better when you have noisy data, tend to behave better in noisy environments where you need some measure of robustness. And these are the reasons why, like the examples I gave before, learning-driven programs are already starting to come to the front. We have all these examples, like in particular spam detectors. I don't know what I would do without a spam detector. So these applications are all over the place. We are not even close to having seen the limits of what we can do. So, for example, this was a machine learning protest in Carnegie Mellon maybe a few years ago. And what I want you to answer is how many people are in this picture?
It's like 5.
I hear a lot of numbers. How many people say more than 10? How many people say there are no people in this 10? Okay, so we have established a range. Okay, who's brave enough to just shout out the answer?
4.
4.
6. 5. 7.
Okay, roughly 4 to 6. I don't see 7, but you know. Roughly 4 to 6. But here's the question. You guys are all amazing at it. But I'm going to argue there are no more than 2 people in this picture. Or 3 at best. Because what I'll do is, let's say I count all the heads. How do you detect people in pictures? One way to do that is to count heads, because you know every person has one head. So this is a head, and there is a tiny bit of a head here, and there's a chin here, and we know that every head has one chin. So there are, option 1, there are 3 people. Clearly wrong. Let's consider another case. Let's count the number of hands in this thing, because we know most people have 2 hands. So we see a hand here and 2 hands here. So there are 3 hands. So this 1.5. Okay, so let's maybe count legs instead, because everyone's got 2 legs, hopefully. No more than 2. There are 2 legs here and 2 legs here, so there are 2 people. I don't see more than 3 people here, and somehow you are able to come up with 4 to 7. So yeah, there are, and yet when I counted 5. And the point is, you know how the world works. You know that this hand here is not attached to either of these 2 people, so at least there are 3 people. You know that there's a head here which is not attached to this hand, so this is a new head. And you know that this bit here, which turns out is not visible in the slide, this bit here, anyway, this bit here, is a neck that doesn't belong to any of the other people, so at least 5. And you're doing sophisticated reasoning about, if I want to think about how I might build this as a program without machine learning, I have no idea. You can build a neck detector, and a hand detector, and a head detector, and a leg detector. But the fact is, these things are not used in isolation. They have to live together and interact with each other and constrain each other's decisions and use in the larger context of any application. So hopefully this gives you an appreciation for the next time Siri or Google Now misunderstands you and takes you to Kansas. Because it's a really, really complicated set of decisions that are being made here. And each of these decisions are noisy and they interact with each other, probably adding to the noise. Okay? At the end of the semester, I don't know if you'll be able to write applications that can actually count the number of people here. And probably that's asking for too much. But hopefully you'll be able to appreciate how you might at least take the first step in that direction. So, while we're talking about applications like computer vision and such things, I think machine learning by itself historically has been related to many, many different areas. I'm biased, and I believe that machine learning grew out of artificial intelligence. And artificial intelligence, if you've seen it before, is this quest to make computers that are intelligent, for whatever that means. And sometime along the way, it became obvious that you can't really build intelligent computers without any learning in the picture. So machine learning and artificial intelligence go way back. But what kind of gave birth to the field, I think, is the understanding that to do anything interesting in this field, we need to be able to formalize these problems, make them well-formed problems. And that connects it to theoretical computer science and mathematics. So we are using tools that we know from analysis, we are able to formalize learning, and we are able to use ideas from probability theory and our understanding of linear algebra to reason about what can possibly be learned. Are there things that cannot be learned possibly? Can you think of an example of a function that cannot be learned? How? Truly random ones. Or how many people have taken a class in cryptography or ever heard of cryptography? 5 people. So, if you believe what's happening in cryptography, you can't. There are functions which cannot be learned. Unless, if they are learnable, then a lot of other things become possible and life is not all that pleasant. Or maybe not, maybe it is pleasant. So there are functions which cannot be learned. How do you identify this kind of functions and not waste our time? The only way to do that is to analyze these things formally, and that pushes the need for a theoretical understanding of learning. Learning is also related to psychology and neuroscience and such things, because that's another way of thinking about learning. Because we have one example of a system that learns, that's the brain, and there are many people in the machine learning community who try to take inspiration from some sort of a cognitive architecture for building learning programs. It has connections to philosophy. What is learning? What does it mean to understand? What does it mean to know? But we won't be answering any of these questions in this class. I think learning has very cool connections to linguistics, but that again might be my bias, because my preferred area of research is also in learning needs language. It has connections to robotics, because if you are building a robot and this robot has to do something on Mars, you can't really program it. So you need to have developed algorithms that can actually let the robot adapt to unseen environments. And there are many applications. We've already talked about some. This artificial intelligence has been one of the biggest applications of machine learning historically. Medicine, I think, is one of the most interesting applications coming up. It's used in engineering all over the places. You might, for example, think about a classifier that decides, based on some measurements, whether this bridge is going to collapse or not. Or machine learning is starting to show up in other areas of computer science. We've seen examples in recent years where classifiers are used within compilers to predict whether certain compiler decisions should be taken or not, certain optimizations. It's used in psychology in very, very interesting ways. One of the oldest uses of these things, or one of the most classic examples, is can a program that's based on learning replace a therapist? And it's used in marketing, advertisements, ads that you see on your computer, maybe in your new Google Glass successor, whatever. So it's all over the place. And what is more interesting is that every one of these applications and these, the sources of machine learning problems are active research areas. And in the coming decades, it will be a very, very hot area. I mean, it already is, but I expect this to be pervasive. So that's about the general introduction to machine learning. Are there any questions? Yes?
What's the difference between machine learning and artificial intelligence?
Good question. Artificial intelligence is an umbrella field that encompasses not just learning but also applications like computer vision or natural language processing or robotics. Learning, I think, is front and center, but artificial intelligence involves bigger goals. Okay, so given this sort of an understanding of why learning is interesting, let's talk about the actual class itself. In particular, I'm going to talk about what are the kinds of topics I'll cover in this class. And this is a somewhat biased set of topics from the entire collection of lectures that I have. It's primarily just to give you a flavor of the kinds of questions that we'll be answering. Most of the things that we do in class fall in one of these 5 buckets. We'll be defining models, defining learning algorithms, we'll be exploring learning protocols, we'll be learning about learning theory, and we'll be thinking about representing data. And all of this through lectures, through homeworks, there's a project, and hopefully also through the exams, hopefully the exams will also be a learning experience. And what do I mean by each of these things? What do we mean by models? From my perspective, when I say model, I mean what is the space of functions that the learning algorithm operates on? For example, when I gave you the example with badges, the names, and I told you that all the labels are a function of the name and nothing else. So you don't have to worry about whether this person, is more than 7 feet tall. You don't, because I told you that the function is only a function of the name. So already I've restricted the search space. You were asked to propose answers that were functions from names to plus or minus. But then that's all. That was the only restriction I gave you, but you biased yourself furthermore. You started counting characters. You started looking at vowels and characters. I said name, and somehow you broke it down into characters. I have no idea how you did that. I never said anything about it could just be the font in which the name was written, but you did not even consider that. So you brought your own knowledge to decide maybe the functions are one of these 18 different things, and let me see if they fit. In particular, we won't be looking at functions from names to plus or minus. We'll be looking at broad classes of functions. We spent a lot of time on a very general class of functions called linear classifiers. We'll be spending some time on something called decision trees. We'll explore nonlinearity a little bit, primarily through something called kernels, and we'll also briefly look at the idea of not just training one classifier, but a whole committee of classifiers, and figure out what's the best way of making them all come to a consensus decision. For all these models, we'll explore different learning protocols. And by learning protocol, I mean what's the interaction between your data and your learning algorithm. The most dominant one is something called supervised learning. Supervised learning is the exercise that we had just before. That is a teacher or an oracle that comes in and labels a whole bunch of data for you, and then leaves the room. And you, as the learning algorithm, or the learner, only get to interact with this oracle function through this data and nothing else. One example could be, say you want to teach me the difference between a road car and a sports car. Trust me, you'll never be able to teach me the difference because I'm blind to that. I don't know why. But let's say you want. And one way of doing that is you give me a bunch of images of cars, 100 images, and you label 50 of them as sports cars and 50 of them as normal cars. And I look at them and I somehow figure out, having seen these 100 examples, what's the best way, whether a new image is a sports car. That's supervised learning. The direct contrast to that is something called unsupervised learning. Unsupervised learning is a setting where there is no teacher. The learning algorithm gets a bunch of examples and nothing else, and has to go learn. It's also called clustering. It figures heavily in data mining. We'll look briefly at this, and if you're interested, if you feel that this is more interesting, I recommend that you also take the data mining class. But in some sense, unsupervised learning, to take the car analogy, you want to teach me the difference between sports cars and road cars. And what you do is you give me 100 images of cars and say, there are two kinds of cars here. Go figure. You don't tell me what is what. And then you give me the pictures, and then maybe it's possible I decide that there are two kinds of cars that are red and all others. but you have given me really no inclination as to, or information about what the labels, what kinds of functions you had in mind. So that's unsupervised learning. In between these two extremes is something that is more realistic. It's called semi-supervised learning. And semi-supervised learning is, there is a teacher, the teacher sits and labels a few examples and then goes away, and you have a bunch of unlabeled examples, and the learning algorithm has to figure out what to do with this whole collection of data. It could be anything. And in some sense, unsupervised semi-supervised algorithms are practically more interesting because they let us deal with the fact that it's really expensive to get labeled data. And I'll keep mentioning this again and again. One of the most valuable resources that you will have in this regime is labeled data. And it's going to be more and more expensive because sometimes we just don't know, we don't have people who can label data. So, quick question, how many people have seen supervised learning before? How many people have seen any of the others before? Unsupervised or semi-supervised? A few. Okay. So these are the top three are three kinds of learning algorithms. Just for the sake of completeness, even though I won't be mentioning this in class, there's another whole family of learning algorithms which come under the umbrella of interactive learning, where the learning algorithm gets to interact with the universe to somehow probe the universe to ask to learn. Active learning is a setting where the learning algorithm gets to ask questions to the teacher, like I'm hoping some of you will. So, if you have a doubt, or if the learning algorithm has a doubt, it can ask, this particular point, I'm not sure how it's labeled, can you help me out? And that's active learning, or interactive learning. And active learning is one of the more interesting kinds of solutions that are developed or it's actually a research problem really. It's an area which lets us ask, it's really hard to get labeled data. Is there any way in which I can minimize the number of labeled examples by asking questions? Another kind of interactive learning algorithm is called reinforcement learning, and this is the kind of setting where the learning algorithm gets to interact with the environment. And the environment could be defined as the physical environment that we are in or some software environment, and then figure out what to do. If you're interested in reinforcement learning, I think one of the AI classes covers it. So I already asked you who's seen supervised learning before. So we'll be covering primarily we spent a significant part of this class talking about supervised learning, some amount of discussion on unsupervised learning, and maybe a little bit on semi-supervised learning as well. In all these, we'll be looking at different learning algorithms. Yes?
Do you have some examples for active and reinforcement learning? Like you kind of mentioned like a brief description of that.
Right, so active learning is, so have you heard of Mechanical Turk? It's an Amazon service. Let's say, I'm going to give you a made up example. Let's say I want to learn whether a certain word in English is, or let's say I want to learn whether this particular word here is correctly used in context. Okay? So, for example, I want a piece of bread and I type PEACE and I want a program that tells me there's a mistake here. It's not a typo because there's no typo. One way to do this is to have people sit down and mark errors. Another way would be for the learning algorithm to pull up a random sentence from Wikipedia, let's say, pick a word that it thinks is misclassified perhaps, or it's uncertain about, and then goes to Mechanical Turk. Mechanical Turk is a service where you can give it inputs and a human will sit and label. For every label that the human gives, you pay some money. And now your interest is not just to learn the concepts correctly, but also to spend as little as possible, because you are actually paying. So this is like a very classic setting for active learning. Reinforcement learning shows up, for example, in robotics. The example of the flying helicopter I mentioned is, if you have time later, you can check out this video on YouTube where there was this helicopter that taught itself to fly. How it went? It learned how not to fall, basically, because there was a significant negative reward attached with falling, and it worked. And this is research that happened in Stanford, and it produces an amazing demo. So check it out. So across all these settings, in particular in supervised learning, we'll be looking at 3 different classes of learning algorithms. One group is called online learning, where the learning algorithm gets to see one or a small number of examples at a time, do something to its internal state of the world and throw it away and keep it rated. In contrast, there's batch algorithms, where the learning algorithm gets all the training data at once and kind of cogitates on it and does things. In the online scheme, we'll be looking at algorithms that are, we'll be looking at 2 algorithms basically, perceptron and winner. And in batch, we'll be looking at a whole bunch: naive Bayes, support vector machines, logistic regression, decision trees, maybe nearest neighbors, and a bunch of others. And we'll also be looking at a couple of semi-supervised or unsupervised algorithms, in particular something called expectation maximization, which is generally, it seems like a good philosophy. And I'll show you, if you've heard of the k-means algorithm, some of you may have seen it. I'll show you that k-means is actually an instance of EM. This is EM. How many people have heard of these names before? Many of you. So that's kind of proof that learning is everywhere. How many people have implemented these before? A smaller number. And how many people have derived these things before? Hopefully at the end of the class you will know how to derive it. One of the fundamental questions that shows up across all these things is the question of where do these examples come from and how do you represent data? Throughout the semester I'll be talking about features. And when I say features, what I mean are attributes of data. For example, features for the name could be its length, the characters in the name. Or features of a car could be its color, its weight, or what fraction of an image it occupies. Or it could be something like, I know this is a 19-something some car, and it has this engine and these things. So basically, attributes of the object that you're trying to classify are features. Who gives you those features is a $1 million question. One answer is that there is a domain expert. A person who knows everything about cars sits and tells you these 21 things are all you need to decide whether this is a sports car or a road car. But a more somewhat interesting and open question, which is an active area of research now, is can I learn these features too? So you have learning to do learning and things like that. Also related in the same ballpark is the problem of dimensionality reduction and principal component analysis and things like that. SVD, for example. What ties all these things together? So I've got like various different philosophical to mathematical points. What ties all of them together, I believe, is the theory of learning. And we'll spend a fair amount of time talking about the theory of learning. And for me, this is probably the most interesting part of learning. There are many different ways of quantifying the question, what does learning mean? And we'll talk about 3 ways of asking that question. One of them is online learning. One of them is the wonderfully named, probably approximately correct learning. And finally, we'll look at Bayesian learning. And it turns out, all these algorithms that I mentioned before just fall out of this theory. This theory also will be able, or these kinds of analysis, they also will tell us, is learning possible? What kinds of functions can be learned? What does it mean to learn? And things like that. And my secret agenda in this class is to point out that if you're able to ask the question of what is learning correctly, algorithms and such analysis automatically comes out of it. So there's either you can learn to fish or you can, I don't know, something about fish. You can teach a man to fish or buy him fish or something. So understanding this theory is like teaching a man to fish. So as far as I'm concerned, this course is about the underlying concepts and the algorithm and the ideas that give rise to the algorithms rather than just the algorithms. What this class is definitely not is a cookbook. I don't want to sell any one particular version of machine learning software. And in fact, I'm hoping that you don't have to use any machine learning software in this class, because you will be you will be implementing learning algorithms yourself. And at the end of the semester, you will probably be able to, you'll probably have your own little library of learning algorithms. And this is certainly not about any one single style of learning, because I want to focus on the general concepts that general questions that you should ask when somebody comes and tells you, I've invented a brand new learning algorithm and it's the best thing ever. And then you should ask, okay, what does it do? How do you know you're right? And we learn how to ask these questions formally. Questions? Yes?
And so in the supervised NZ case, why do we provide the example? Why don't we define, for example, in your sports car, why don't you define what the sports car is?
How do you define what a cat is? For example, let's go back to in the image that I had before. If you're able to define what a person is, the problem is solved. A person is a neck and two hands and two legs, but maybe sometimes the neck is not visible. Maybe sometimes the two hands are not visible. Sometimes you just see a little bit of the hair. So there's so much noise. Typically, in the problems that are perfectly suited for learning, defining the problem is really is not easy. So if you're able to define the problem, I would argue the problem is kind of solved. So what will you learn in the semester? As I said, you'll get a broad overview of learning, and I personally like to balance the theoretical and the practical side of things. So you'll be doing a fair bit of math, and you'll be doing a fair bit of programming. Come to think of it, you'll be doing a fair bit of work. And at the end of it, you'll be able to implement learning algorithms. And through experience, through your homeworks and project, I hope you'll be able to get an idea of where learning can be applied. What kinds of problems are perfectly suited as applications where learning applies. Next question is, how will you learn? And that's really a question about course information and logistics, and that takes us to a totally different presentation. So, give you an overview of the class. Let's talk about the more mundane aspects. This class has a website because we are in the 21st century, and you can find it if you Google for it, or you can visit my website or something. You should have found it by now. We'll be using Canvas as a discussion forum, and also we'll use Canvas for homeworks, submissions, and grades. If you've not noticed it before, there's a camera in the class. This class is being videotaped. If you have any objections to being in a room with a camera, please come and talk to me, and I'll talk you out of that. And the lectures, video lectures, will be posted on the class website eventually, and I'm afraid to commit what eventually means, but not too far from actual lecture. We'll use Canvas for managing all the submissions, as I said, homeworks, and basically homeworks. Who's involved? Who are the people involved? There's me. And we have lectures on Tuesdays and Thursdays. So is it Tuesdays? Yeah, Tuesdays and Thursdays from 2 right here. So if you made it here, well done. And except for the people who are actually remotely available, remotely watching this, so they know, if you are remotely watching this, you know how to get to this lecture. You can get information about where my office is and stuff on the class website. And I'll have office hours right after class in my office. There are 3 teaching assistants. There's Nick and Jingwan. You guys stand up or something. And they have office hours too. The third TA is Abhinay, who is currently out of town, and we'll meet him maybe hopefully next week. So the office hours, my eventual goal is to have one office hour every day of the week, and we are close to realizing that. We'll be using Canvas, as I said, as the primary medium of communication. Please use Canvas for discussions, because if you think you have a question, I bet half of you have the same question. So by using Canvas, you're kind of not just learning but also doing a service. If you email us, you should prefix the email subject with the course number, because there's, yes?
The last TA used to at 4:30 in the morning.
Good question. Srikumar, do you want to do 4:30 in the morning? Well, looks like not. So, yeah, 4:30 p.m. Good catch. There might be mistakes in the slides, and please point out. It occasionally leads to humorous responses, and more often it will lead to corrections, and you'll learn better. So if you use email to contact us, expect the response time to be slow. If you have a pressing question, use Canvas. Unless it's of course something personal, in that case, of course, email us. Feel free to contact us. Yes.
Approximately when do you post the video lecture?
Maybe a week or two from the actual lecture. I'm not sure. We're still working on the logistics, and I'm hoping it will be around that ballpark. Yeah, and there will be announcements on the class website, and we'll try to mirror those on Canvas as well. So, how will you learn? And everything I have in these slides, there's like volumes of text written about it on the class website. So I encourage you to read what's written there. And anything that's here and the website is the final word on this. So I mentioned this probably to many of you when you contacted me. If not, I'm telling you now. This class requires a fair amount of understanding of linear algebra, of some basics of probability theory and statistics, and you should be able to look at an algorithm and implement it in some language. If you have trouble with that, there are some resources on the class website that will probably point you to the right answer. Yes?
Do you have a preferred language for our assignments?
For myself or for you? For your assignment?
Us to use.
I don't.
Grading.
No, I don't have a preferred language, but I do absolutely insist that any programming assignment that you have must run on the CADE machines. So if you've not used CADE before, please familiarize yourself with how to log into CADE and be able to run things. And the TAs who are running these things will not install some special software for you. So basically it should work in the CADE environment as is. And it should be a single line run script. There will be more information about this as the assignment comes along, because in some sense, if you want to use Julia or Rust or something, go for it. But if you use a language that none of us know, I'm not sure how we'll be able to help you with that. So, if you're using a esoteric language, we can't help you necessarily with the implementation. If you're using probably between the TAs and me, we probably know about 8 or 10 languages. And they are the usual suspects that you can imagine. Okay? And there are no required textbooks. There are a bunch of machine learning textbooks that are out there. I've listed some of them on the class website, on the resources page. I don't insist that you buy any of them, but I believe that if you're thinking of actually continuing a career in machine learning, if you're doing research in this area, then probably eventually you'll need these things. But for now, just try it out. You don't need to buy a textbook. The class is self-contained. And any material that, any reading material that I post, I'll try to make sure that it's available. If not, I'll try to make sure that there are multiple versions that you can read, not necessarily from one textbook. I am growing a collection of resources, and if you feel that there is this amazing lecture on linear algebra that taught me everything I know that should absolutely be made available for the rest of the class, send me an email. I'll add it to the website. If you want, I'll even put your name next to it. Or not, whatever. Now about grading, yes. So there will be homeworks, there will be exams, there will be a project, all the good things that you can expect in a class. Your homeworks and quizzes will account for 36% of the grade. You will have 2 exams, a midterm and final. The midterms will be in class. final will probably also be in class. I think the dates are on the class website, and they'll together account for 40%. And all of you will be doing a final project, and that will be about a quarter of your grade. So let me talk about the homeworks first. 5 or 6 homeworks in all, and roughly 2 to 3 weeks apart. Because this class has both grad students and undergrads, and I don't necessarily want to labor the undergraduate students way more than they need to, grad students will have to do extra work. And it's not bad. How many undergrads are here? Oh, more than I thought. I must tell you though that in the previous incarnation of this class and similar classes that I've seen before, undergrad students have done better than most of the grad students, and sometimes all of the grad students. So you guys have a good legacy to live up to. And the grad students, you guys have to step up your game. So either way, it's going to be fun. And I will not accept any handwritten solutions or scanned solutions. I say digital and I mean typed. LaTeX is wonderful, or if you feel that you will not use LaTeX, you can use Word or something, but please do not make us read your handwriting. My handwriting is among the worst in the world, and I know yours is equally bad. So let's just make it easy on each other. So, and the homeworks have a late policy. We'll give you 24 hours after the class submission, official submission date, exactly 24 hours. For you, we'll leave the submission window open, and if you cross the official submission time, you lose 10% of the grade for that exam, for that homework. If you cross 24 hours, then you get 0. So if the night before the deadline, if you're writing the homework, you get an option. You get to decide. Are you willing to sacrifice 10% of the grade and get 24 hours extra, or are you willing to submit it as is and maybe get 10% less? It doesn't. And we're going to be very strict about this. Previously I was not so strict, but this time I've decided we're going to be, if the deadline is midnight, 12:01 counts as the next day. And we'll use the timestamp on Canvas for this. Questions? Yes?
How many homework will be programming and how much will be like short answer?
I'm going to mix them up. At least in the beginning, all homeworks will have both theory and programming. Because in some sense, this is one of the coolest things about machine learning. You can't really learn learning without implementation. You can't really learn it without math. So we'll try to mix up both. As the semester goes along, maybe the homework will become more theory heavy. But I expect almost every homework to have a little bit of, at least quarter of it will be a programming section. The other thing that you'll do for the class is projects. And there's a lot of stuff about it on the class website. And even though, I don't want to make this a big onerous task, I want you to have fun. In some sense, the goal is to show yourself, me, everyone, your cat, what you've learned. And apply what you learned to something that's interesting to you. If you believe the most interesting problem in the world is to classify, hardware in a hardware store, let's see if we can write a classifier for that. And make it interesting not just for you but also for me, and if possible, maybe I'll also learn something about something new that I've never seen before. So be creative about your projects and we can talk about it. We'll brainstorm ideas, we're all available to talk to you about projects. There are some ideas for projects on the class website. And if possible, if you're already working on something that involves machine learning in your day job or research or something, and you feel like you want to take a slice of it and make it a class project, I'm all for it. I expect the project to be done in groups of either 1 or 2 students. And there are several milestones that I've divided this thing into. And one of them is coming up, what's the date? September 15th, when all you have to do is tell me by email what your project group is, okay? Whether you'll be doing it by yourself or which 2 people will be doing it together. So you have to form a project group by September 15th. Other administrivia or collaboration and cheating. Generally don't cheat, actually never cheat. I strongly encourage collaboration. I strongly discourage cheating. Collaboration is when you learn from each other and both benefit. Cheating is when only one person benefits. If you use, and there is a school of computing policy on cheating, I'm assuming all of you have seen it, heard of it. If you've never heard of it, you probably have not heard that, at least for grad students, you have to sign a document and something like that. So, if you've never heard of this, then you may have to sign something and give it to the front desk. If you use any resource or any source of any book or paper or anything in your homeworks or projects, be nice and cite them, because that's academically good. That's good academic policy anyway. And absolutely, your homeworks and your projects should be your own. And obviously, I don't encourage collaboration or cheating in the exams. And if you need any help with accessibility and stuff, just come and call me. Send me an email or come talk to me, and I'll do everything I can to help you out. The other thing I want to really know is who you are. There's like a very diverse mix of you in this class. I don't know most of you. Actually, I recognize only a small number of faces, so I'm really curious. So there's a quiz on Canvas. It's not a quiz for points, it's a survey. And we just ask questions like, who are you, what do you want to do, why are you in this class, and such things. If you've never filled out a survey like that with me before, please do that. And it's not that I'm snooping on you or collecting information, I just want to tailor the material in the class so that I can suit it to your interests. If you care absolutely about building an image recognition program, tell me. And I'll try to introduce more examples that have to do with image recognition. So I think I'm almost at the end of this. Any questions for policies, homeworks, exams, programming? Yes.
Where are office hours going to be held?
We'll figure that out after the class.
Okay.
Yes.
So, what's the difference between machine learning and pattern recognition?
It's a new name. That's pretty much my best guess at this point. I have not figured out the difference. If you learn the difference, tell me. As far as I'm concerned, it's just a rebranding. Yes?
For the projects, do we have to give a presentation or just a report?
I don't. Logistically, it seems impossible to have a 90 presentations in class, so it'll just be a report. Maybe there might be a poster session, but I haven't decided on that at this point. But there will certainly be a report. There will be, in fact, multiple reports, don't worry. Other questions? Oh, and one more thing, I've saved the last thing, the best thing for last. There's a homework. First of all, many of you came to me with questions, or some of you have still got to figure out issues with registration. If I'm still working on that, and if you're still waiting to register for the class, hopefully things will get ironed out by the end of next class. If things don't get worked out by the end of next class, send me an email. There is a quiz called Quiz 0 that's on Canvas, and it has nothing to do with anything that I've said today. It's everything that you already know, or hopefully already know, and it's mostly just what I think of as early college or late high school math. So you take a look at it. It should not take you too long. If you're really struggling in that exam, in that quiz, then you should think about taking this class, whether or not you should. It's mostly to refresh your memory and take, if you feel like everything works out but something is not, I have never heard of this thing, maybe you can learn that concept by looking it up. And that will also force you to find a bunch of sources and go over the sources. And this is due maybe in a week or something. And it's on Canvas, you should be able to access it right now, I think. If not, we'll figure it out. And I want to remind you to fill up the survey. And I think that will also be open for a week or two, and it's completely optional. If you don't feel like spending the 5 minutes filling up a survey, don't bother, but the quiz is not optional. Alright, if there are any other questions, I'm around. The TAs are around, otherwise I'll see you next class.